Welcome back to Solids and Liquids. In part 2 of this unit, we're going to be talking about the effects of intermolecular forces, what intermolecular forces will do, or what properties they will cause. Now, when intermolecular forces are greater in a substance, the atoms or molecules in that substance exert greater attraction on each other and seem to stick together better. Stronger intermolecular forces equals stickiness. So the following properties that we're going to talk about are all properties that tend to be influenced by intermolecular forces. The first property we have is surface tension. That's a force that pulls the surface of a liquid together due to uneven pulling on the surface molecules by the interior molecules. This is what causes water droplets to take on a spherical shape to minimize the surface area. So let's say in this water droplet, on the surface of the water droplet, the water is attracted to, one water molecule is attracted to other water molecules that are only below it. So that water molecule as a whole is going to try to burrow itself in deeper. Whereas some molecule that's in the center is going to be attracted in every single direction, so it's not particularly moving anywhere. So all of the molecules on the outside are trying to get into the center, and all of the molecules in the center are pretty happy. So it gives us its spherical shape to try to minimize the surface area. This over here on the right is a picture of mercury. It tends to form little droplets or beads that'll kind of roll around because it has a really high surface tension. And substances with stronger IMF will tend to have a higher surface tension. High IMF equals high surface tension. And so mercury has a higher IMF than water because it beads up more than water does. And water has a higher IMF than, say, alcohol because that is totally like flat. If you were to pour out alcohol, it would be totally flat. It wouldn't bead up at all. The next property we have is capillary action. That's the ability of a liquid to flow through a narrow tube due to adhesive and cohesive forces. Okay, so adhesive. Think about adhesive tape. That's sticking one thing to another thing. So, for example, water attracted to a glass tube. And then cohesive forces, that's forces that are within. So that's water attracted to another water molecule, for example. Well, if you have a very narrow tube and you set it in a little bit of water, the water will just go straight up the tube. That's capillary action because the water is attracted to a tube. The water is attracted to the glass. And that's what gives water itself a concave meniscus. The water's kind of hugging on the sides of the glass because it's more attracted to the glass than it is to itself. So it gives it a concave meniscus. The opposite is a convex meniscus. For example, mercury, which is attracted more to itself than it is to the glass tube, it has greater cohesive forces rather than adhesive forces, so it gives it a convex meniscus. And if you can tell these pictures on the right, these are actual pictures of water and mercury, you can kind of see that this water has a concave meniscus and the mercury has a convex meniscus. The next we have is viscosity. That's a measure of a liquid's resistance to flow. Molecules are resistant to flow because there's a great attraction between them or strong intermolecular forces. Viscosity decreases as temperature increases. Viscosity decreases as temperature increases. And that's because the additional kinetic energy is counteracting and breaking the intermolecular forces. So high intermolecular forces mean strong viscosity. And when it's heated, it becomes thin as the intermolecular forces are broken, and so the viscosity is lowered. A good example of something that's very viscous is honey. And over here on the right, I have two different types of oil. This one on the bottom has a low viscosity. You can tell it's dripping very quickly, whereas this one on the top takes a lot more molecules or more larger drops because it's much thicker. Next we have evaporation, which is vaporization that occurs only at the surface of a liquid. During evaporation, the more energetic particles escape from the surface, leaving the less energetic particles behind. From the surface only is evaporation. So evaporation rate versus IMF. As the strength of IMF increases, so greater IMF, evaporation rate decreases. We have to say evaporation rate because all things will evaporate if given enough time. But the rate of evaporation will be lower. It will take longer time to evaporate because the molecules are held together more tightly and they're less likely to escape into the gas phase. Evaporation rate increases with temperature increase due to the increased kinetic energy breaking the IMF. So increased temperature, which is your next little thing, evaporation rate increases. Also, evaporation is a cooling process. As energy is required to break IMF between the molecules, that's why sweating is going to cool off your skin. Energy is absorbed into the sweat droplets and therefore released by the skin so that the sweat can evaporate. So when something's evaporating, it has to take in energy to break the intermolecular forces, and if it's taking in that energy off of your skin, then your skin is left feeling cooler. The next we have is vapor pressure. That's the pressure exerted by a vapor over its liquid. The more of a liquid that evaporates, the more vapor that's present, which causes a higher vapor pressure. So particles with high enough energy can escape from the surface of the liquid. And so these form a vapor above the liquid surface, and that is your vapor pressure, the pressure of the vapor over its liquid. We have equilibrium vapor pressure. That's the vapor pressure that's exerted when a gas is in equilibrium with its liquid. At equilibrium, the rate of condensation is equal to the rate of evaporation. So notice here we have a closed container, a closed flask, and you've got water in this flask, and so the water will evaporate. And slowly the empty space above will have water in it. And so now you end up with a whole bunch of water molecules, and some of those water molecules are going to start condensing back into water, and some of them stay up as a gas. And when the rate of water molecules evaporating is equal to the rate of water molecules condensing, you have equilibrium. The rate is the same. It does not mean that there's the same number of molecules on each side or doing each thing, just that the rate is the same for each thing. So vapor pressure versus IMF. As IMF goes stronger, increased intermolecular forces, less liquid will evaporate. As there will be less vapor pressure, there's going to be in turn less vapor pressure. The stronger the molecular forces, the less it will evaporate, which means less vapor, and therefore lower vapor pressure. The relationship between vapor pressure and temperature, as kinetic energy increases, Ke increases, so temperature increases, the intermolecular forces between the molecules is going to decrease. It's going to pull the molecules apart. This will allow more liquid molecules to escape to vapor and raise the vapor pressure. So vapor pressure increases. As kinetic energy and temperature increase, vapor pressure will increase because more of the molecules will evaporate. Alright, our next one is boiling point. That's the temperature at which vapor pressure in a liquid equals the atmospheric pressure. And so we were talking about evaporation a minute ago. The bubbles cannot form since the vapor pressure is less than the atmospheric pressure, so it's only escaping from the very surface of a liquid. But when you're boiling, the bubbles can form within the middle of the liquid. The bubbles can form anywhere, all of these bubbles, since the vapor pressure can overcome the atmospheric pressure. So imagine the atmosphere is a giant blanket pushing down on this water in the beaker, and the bubbles can only escape when they have enough energy to overcome the atmospheric pressure. So next we have boiling point versus IMF. As the strength of the intermolecular forces increases, high IMF, a group of molecules will require more energy to enter the gas phase. This means that more energy will have to be absorbed for vapor pressure to equal atmospheric pressure, and so stronger IMF will relate to higher boiling points. Stronger IMF will relate to higher boiling points because it takes more energy to break apart those intermolecular forces, and so it's going to get to a higher temperature before it does. For boiling point versus elevation, as elevation increases, atmospheric pressure decreases. Notice that these are going, atmospheric pressure is going down as elevation is going up because you have less of that atmosphere blanket on top of you. This means that the required vapor pressure needed to overcome the atmospheric pressure also decreases. Therefore, less kinetic energy is needed for the required vapor pressure to be reached, and the boiling point is lower. So the boiling point of water in Denver, Colorado is about 94 degrees C, where here, this says Boston, but we're going to change it to Houston because we are also at sea level, is 100 degrees. If you were to go to the top of Mount Everest, which is the highest mountain peak on Earth, the boiling point of water would only be 78 degrees. So a high elevation means a low atmospheric pressure, and if we have a lower atmospheric pressure, we have less to overcome and therefore a lower boiling point. Next we have the heating curve, and the heating curve is the same heating curve that we used in thermochemistry, the thing that looks like this with the boiling and the melting and the condensing and freezing and all of that. But here we're going to relate that to intermolecular forces. Starting with melting point, that's the temperature at which the forces holding a solid lattice together are broken, when breaking apart a solid. When enough energy is applied, intermolecular forces in a solid are weakened, and the solid melts. So in a compound that has strong intermolecular forces, more energy is required to weaken them, and the temperature for melting is higher. The heat of fusion is the amount of energy required to break 1 gram or mole of solid into a liquid, or the amount of energy released when a liquid turns into a solid. In a substance that has really strong intermolecular forces, more energy is required to melt, and so the heat of fusion is higher. Specific heat is the amount of energy required to heat 1 gram or mole of a liquid by 1 degree Celsius, or to cool the amount of energy released when 1 gram of a liquid cools by 1 degree Celsius. In a liquid with strong IMF, more energy is required to heat the substance, and the specific heat is higher. And finally, we have the heat of vaporization. That's the amount of energy required to boil 1 gram or mole of a liquid at its boiling point, or the amount of energy released when 1 gram of a gas is condensed. In a liquid with strong intermolecular forces, more energy is required to boil the substance, and the heat of vaporization is thus higher. Let's look at the actual heating curve and relate it to. So this is the same heating curve as you saw before, but in this case it is to scale. When I was typically drawing the heating curve in our thermochemistry unit, I made these lines the same length just because that was easiest to do and easiest to draw. But really the solid and liquid lines should be much smaller, and the liquid and gas line should be much larger. So this is not to scale and not quite right. So this shorter line indicates that there's less heat required for the transition. The longer line indicates that more heat is required. Going up the curve requires energy, so boiling is endothermic. Going down the curve releases energy, so freezing is exothermic. Going up is endo, going down is exo. And we could also have a cooling curve, which is the same thing as a heating curve, just written backwards, where we have a gas that's cooling, and then we have condensing. Then we have a liquid that's cooling, and we have freezing, and then we have a solid that's cooling. So you could do the same thing with a cooling curve and not just a heating curve. Alright, so those are properties that are affected by intermolecular forces. Join me next time when we talk about types of solids. See you then.